Okay, let me check the microphone setup. First of all, we have 23 students connected, and I check up for the microphone is it's Jabra, okay. What I've done. Okay. Jabra, okay, let me see this one. Good afternoon, guys. Okay, then I go to share my screen. Okay, so name, this is class of applied econometrics. Econometrics, but audio should be Jabra. Yes, Jabra speak. Class of econometrics. Okay, you will see that. I have to select this one, and I think I should be able to start. I will say so. So can the people connected at home see my screen?
Yes.
Yes.
Okay.
Yes.
You can hear me and you can see me. Okay. Unfortunately, it seems that only one camera is working, only this one. Let me check again if I can change it. I would like that. I don't think so. No, I just. Okay. Okay. So we have just one camera and we have to stay with this one. So I start with the registration. Welcome to our class of applied econometrics of Tuesday. Today is 22. Okay, so I want to come back. I want to. Today the change of room has been quite shocking for me. I don't like this room, I have to say. Now I'm trying to upload all the material, blah blah blah. This morning I sent you something by which I want to complete. Okay, those are the slides, then program. Okay, and finally what I have sent today. Today I've sent you a file. This file which is related, connected to what we were saying yesterday. I want to complete what we were saying yesterday. I have I can't see part of the class because of the monitor. Just give me some time to adapt to this situation. Okay, I will. Okay, I will not see many students behind my monitor. Okay. Anyway, so we are working here. We are. What I want to do today, before going on, we are. Yesterday we closed our class with 0.5 properties of the Euler estimator in the classic linear regression model, but I want to close these 3 and 4 with the following example that we were discussing yesterday. And the best way to do it is to discuss the following example of environmental Kuznets curve with heteroscedasticity. So I sent you this file this morning along with the following Gretel dataset, okay, that we'll discuss very quickly. So this is a very important exercise, because if you understand this exercise, it means that you are doing a lot, okay? So let me consider the following example. Imagine in the data set I have sent you, one check with this, let me do final check with Panopto. Okay, it seems it is working, okay. So coming back on full screen, okay. So we have, imagine that I have a cross-section of data. I have 11,748 Italian households. So I have cross-section data. And so I is an index which runs over households, so individuals. And for each household I observe the following quantity. I observe the, say, per capita log, the log of per capita CO2 emission in tons of the household. Okay, those are real data. Okay, those are real data. Is it possible to close the door? Thank you very much. But if you we can wait. We change the air, then we close it. So let's give 10 minutes, then we close. So I was saying the log of CO2 emissions in tons, and then imagine that, say, no, not imagine. The second variable we observe on the family is total household expenditure, okay? The log of, and this is a proxy of, well, it's not a fantastic proxy, but it's a proxy of household income, okay? And the objective of the analysis, because we all the time we run a regression, something like that, we should have in mind a purpose, okay, for doing the, and the purpose is fundamental to decide what to do. I want to establish whether, say, what might be the impact of a carbon tax on CO2 emission. I would like to see whether a carbon tax which reduces income, what is the impact on CO2 emission. And the model we are considering, that I said, you will study Kuznets curve. You will say, Professor, this is not a curve, what you are estimating now, right? Let me consider a linear approximation of a Kuznets curve. You will, there is a mistake here. Kuznets should be written like this, okay? This is correct, this is wrong, okay? But it doesn't matter. So I have this model where I explain log of CO2 emissions across the n households. As a function, I have a constant, I have an intercept, and I have the log of total household expenditure, which is a proxy of household income. So the model can be written like this, okay, where the xi vector of regressors includes 1, because I have a constant. The regressor I have here is 1. And then x2i, okay? And imagine that my assumption is, I know that I'm pretty sure that there is some heteroscedasticities of different variances in my data set. So the expected value of the variance, depends on the index I, okay? Depends on the household, which it's quite reasonable. And we know that the implication of this assumption is that the big sigma matrix will be something like this. So we have uncorrelation of diagonal terms at 0, but we have different elements on the main diagonal, okay? From our theory, the theory we developed yesterday, we know that the optimal estimator of the parameter beta in this case, since the big sigma is not it's diagonal, but the big sigma has different elements on the main diagonal because of the heteroscedasticity. We know that in this case, the OLS estimator is no longer the optimal one, but the optimal estimator in this case is the GLS, okay? And this is the expression of the GLS estimator. So the GLS requires the knowledge of the big sigma inverse, so the knowledge of the variances I have on the main diagonal. Please let me remind you that these variances are simply, this is the variance of the error term of the first household. This is the variance of the second, of the error term of the second household, and so on until household 11,748. Okay? In this case, we have a large sample because n is equal to 11,700 blah blah blah. Okay, so we can, the approximation that n goes to infinity, it's quite good, quite reasonable in this setup. Okay, now we know that the estimator we should use in this framework is this one, and we know that the standard error, we should take the standard error from this variance covariance matrix. But the problem here is that we don't know the sigma square 1, 2, 3, blah blah. Okay, so that's why we say it is a virtual estimator. So one question is, what can I do now? And it is exactly what I want to discuss with you. The first, imagine that I have, say, I haven't a clue about, say, the first solution. I simply estimate this model by OLS, and as I told you yesterday, I robustify standard errors. And that's the end of the story. I just give up in modeling the taking any stand on the heteroscedasticity. Okay, so let's see in practice. I open the, I have to set it in English and to increase font, blah, blah, blah. So preferences, language, English. Okay, close, I have to close it and start it again. Now it will be in English. And now I increase the font. So tools, preferences, font scale. Yesterday 14 was fine. Let me put 15. Okay. So can you see my screen? Or do you, okay, I increase a little bit. Okay. Tools, preferences, font scale. Let's go for 17. Okay. Even a little bit more. Font scale 20. We should. Okay, 20 is fine. Okay. So the model is I find that the log of CO2 emission is this variable here, 11. The log of household expenditure is this one. So I simply model ordinary square and I say, okay, this is a linear approximation of a Katznet curve, which is you will study it. It's not my job now for the moment. For me, just an interesting example. So CO2 emission is the dependent variable, and the log expenditure is this one. So I for the moment I don't select the robust standard error. I simply estimate this model, and I get this estimation output, which says, you can see that I just gave the intuition yesterday. When you find many stars here, it means that or if you find a T ratio which is large, say larger than 2, for instance, it is our case. You can imagine that, say, the ratio between the estimated coefficient and its precision, because standard error is a measure of variability of my estimate, it's quite good. Okay, we'll say that this 0.6, this is the 0.62, which is the parameters we are interested in order to decide whether to tax or to impose a carbon tax or not. We imagine that for the moment we believe that this estimated model is a good one. Okay. So the estimated coefficient one, the important one, this one here, the beta 2, okay, the beta 2 estimated with OLS is 0.62, okay, which says that 1% increase in household income implies 0.62% of CO2 emissions. So there is a quite tight connection between CO2 emission and households' income, which means that, say, a reduction of household income by taxation could, to some extent, reduce at least of 0.6% the emission of CO2. In this sample of 11,748 Italian households. Now, we said yesterday, the first check I do, I test for heteroscedasticity. I apply the Y test for heteroscedasticity. I have estimated the model by OLS. I want to check if I have homoscedasticity, which is what OLS implies. So I run the Y test, and I immediately recognize by looking at the bottom part of the test. We look at the upper part later on, not now, but according to the mechanical rule we said yesterday, but we have to understand this mechanical rule, okay? We have to do some work, but for the moment, the mechanical rule is that the test statistic is 38.88 with a p-value of 0.0000, so the mechanical rule is that the p-value is smaller than the tolerance level I prefix before running the test, which is typically is 5%, 0.05, okay? So I reject the null hypothesis of homoscedasticity. And so what to do? Can I improve my inference? Yes, one way is, at this point, if I have not a clue, if I have no idea about which variables, how to explain the different variability across the Italian households, what I can do is simply I give up and say, okay, let me little bit robustify the inference. So I modify my model, I re-estimate my model by flagging robust standard errors. Now we know from the theory we developed yesterday, we know that the standard error will be taken not from the usual variance covariance matrix of the OLS estimator, but from the variance covariance matrix of the OLS estimator in the model with heteroscedasticity, which is quite different. So our idea is that we can improve a little bit the inference. So I click OK, and it's interesting to compare. Or I put like this because look at the what I can notice here. Oh, okay, you immediately recognize that the column coefficient does not change because the OLS estimator, it's always the OLS estimator. We find some changes, but apparently not very large one from ABAL econometrics, okay, looking with our haze. And also the standard errors do not seem to change very much in robustifying the inference. So we might be tempted to, yesterday I said the Y test is you can interpret the Y test as a kind of statistical distance between the standard error you have here and the standard error you have here. But I mean, it's a statistical distance. So apparently if we don't take into account, say, the variability, they look very similar, but the test says we have rejected homoscedasticity. So they are, from a statistical point of view, they are different, okay? But I don't see a very large, so basically I have to, if I have no idea about how to model the heteroscedasticity in this setup, I have to use the following estimate, and I will look at the following t-ratio. So if I want, for instance, if I want to test, let me anticipate a little bit. If I want to test, for instance, that this coefficient in the population, this is the beta 2 hat. I want to test that the level of beta 2 in the population, for instance, is 0.7. I will run a test, but we'll discuss seriously. It is part of our program, but let me just give you an anticipation. I want to test a linear restriction on the parameters, and according to notation by Gretel, so the second parameter, second coefficient is small b, b2 minus, I said I want to test whether that coefficient in the population is equal to 0.7, okay? This is the restriction I want to test on the beta 2 parameter. Click OK, I get this result, and let's apply again the rule of thumb we are using for the moment, the mechanical rule. So I have a test statistic for that condition, where I have an F which is 55.63 with a p-value which is 0.0000. So again, smaller than 5%. So I have to reject the null hypothesis that the coefficient is 0.7. Okay, but you will be perfectly conscious of what I'm doing here. You have to wait a little bit. Okay. Now, the purpose of our exercise today, there is some comment from the chat probably. Sorry, Professor, why do we use log of CO2 emission instead of CO2 directly, as in the total? Okay, this is a wonderful question, because econometricians all the time use log, when possible, of course, logs of variables, because if you have a log, the main reason is, there are two main reasons. The one is that by applying a log, you don't change a variable, you simply change the scale. Okay, you know from calculus that the log function is just a monotone function, so you are not changing the value of a variable, you're simply changing the scale. So you are basically, if you have say billions, taking logs, you get something like 10. Okay, so you're simply compressing the scale. And the second advantage is that the interpretation of the coefficient, because in this model, if I have logs here and logs here, the beta 2 coefficient is immediately the elasticity of CO2 emission with respect to income. It's just an elasticity. And one thing that I see typically when you work on your thesis, so I see the very big, say, the naive thing that, say, people who does apply work is not taking logs of the variables when doing econometrics. And that is something that makes me crazy, having coefficient which are billions with standard error, use standard error. The logs, you need the logs in order to have something which is immediately interpretable. The 0.06, sorry, let me come back on the, okay, this number, this estimator is just the elasticity of CO2 emission with respect to income. That's the end of the story. And I don't have strange, huge numbers here, which are not interpretable. So coming back to the very important point by Christina, is that we typically have to do log transformations on variable to compress the scale when it is possible. Of course, if you are dealing with a negative variable, you cannot apply the log. If you are dealing with, if your variable is a percentage rate, you don't apply the log typically. Okay, you apply the log to variable like CO2, tons of CO2, GDP, industrial production, expenditure, blah, blah, blah. But especially you do that when you can interpret by having, say, by taking logs, you can interpret coefficients as elasticities. That is wonderful, okay? So please, when you go on with your work, empirical work, with your activity, remember what I said today. Take logs of your variable when possible. The log is not changing your variable, it's simply changing the scale and improves the interpretation of your results. Okay? Thank you, Christina, for your question, which is important because it is a mistake that we should try to avoid. But I also understand that it's one say, why should I do the log? You will understand that if you do many empirical analysis at a given point, you will realize that it's impossible not taking logs of the variables. Okay. For the moment, please believe me. Now, let me come back to the, this is the inference that I do by robustifying the errors. But let me come back to the point, to the exercise today. I go full screen again. Now, imagine that, so I know that what I have done was I have computed in this model, the optimal estimator is the GLS, but I gave up and said, okay, I go for the GLS and I robustify the standard errors. Now, but I know that the optimal, the efficient one would be this object here. Now I want to say something more. I want to try to attempt to model the heteroscedasticity I have in my data set of Italian households. And let me consider now the following assumption. So how do we model the heteroscedasticity? Let me consider the following assumption and say, okay, I make the following hypothesis. I say that the variance of the error term of household I is actually depends on the regressor, on the second regressor of the, in particular, on total expenditure. So I should have put x2. Okay, so replace this xi. I've written this morning very quickly. So this should be x2i. Okay, the second regressor. Okay, and I take the square of the second regressor. So I'm taking the square of the log of total expenditure. Okay, h is a constant, positive. And of course, I'm taking the square because I want variance to be positive. Okay? You might say, one thing that you might do is, well, Professor, at the end of the day, if you go on the data set, and you look at log expenditure of the 11,000 family, blah, 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 blah. You can see that the advantage of taking the log. I have 11, 10. I don't have billions. Okay, so you can see that they are all positive numbers. So strictly speaking, I would not need, but you don't know. I mean, it's just I'm following a general rule. Okay, but the knowledge that all expenditure, household expenditure, is a positive number. At most, it is equal to 0. Okay, in a very special, in a very extreme case. Okay. But it will give us some advantage. But let me be more, say, as general as possible. So I come back full screen again. So my assumption is that the variability, the variance, is explained by what? By the square. It's a function of household expenditure. The larger household expenditure, the larger will be the variability of CO2 emission. Is it a good assumption? I don't know. It seems quite reasonable to me. But now I want to discuss with you what is the implication of this assumption. So I'm thinking to the problem now. I'm taking I have the Kuznets, the linear approximation of the Kuznets curve, and I'm also taking a stand on why do I have heteroscedasticity. And according to my model, the heteroscedasticity is driven by, say, expenditure, household expenditure. And under this assumption, so the big sigma, which was like this, that will be sigma square 1 will be h, x1, so this is log expenditure of household 1 squared. The second guy will be h times the log of total expenditure of household number 2, and so on. Okay, so I have what I've done. The trick was that now this unknown element is a function of a variable x that I can observe. Okay, and so let me write this big matrix again, like you see I have the scalar h, so I can shift the h outside, and I have a diagonal matrix with where on the main diagonal you have the squares of log expenditure of the 11,748 households. And let me call, just to simplify, this big matrix capital V. Okay, so I have the big sigma turned became H times scalar H times the capital V matrix. Okay, guys? And now we get some fun. Why? Because let me come back on the expression of the GLS estimator I had before, which was not computable because we don't know the variances. But now, what I can do, the natural thing I'll do, I will replace the big sigma with this expression here. And please, the big V, we know the big V matrix because we have data inside the big V matrix. The only unknown element is the scalar A, the proportionality H factor, which is a proportion, say, in my hypothesis, the variance of the household I is just a proportionality factor times the square of the log of total expenditure. Okay, guys? Now, what I'm doing, I plug in this expression, I replace the big sigma with this expression in the GLS formula. I'm applying and I'm computing a feasible GLS estimator. So it's a novelty in your life. No longer we are moving away from the OLS. We have a new estimator, guys. You should be happy. You should be happy. It's a great day today. Of course, I'm joking, okay? And you immediately see that, okay, I have big sigma inverse, I have H capital V inverse here, and I have big sigma inverse, so I have H big V inverse here. You should recognize that because of inverse here, inverse here, and inverse here, the constant, the scalar H simplifies, disappears. And so I end up with this expression here, which I call feasible GLS, because now, if I am good in programming, if I know if I have my data in the big X matrix, if I have the big V matrix, I can compute it. I have a number. And one of the points will be, but can I do that with Gretel? Apparently, there is no option in Gretel feasible GLS. Now we'll see in the next set of page, we'll see that we can do also that in Gretel, and that is the magic, okay? But for the moment, you have to follow me in this reasoning. So this is I have a feasible GLS. The point is, I am computing the efficient estimator of the elasticity of log of CO2 emission with respect to income, because it incorporates the heteroscedasticity. Of course, under my assumption. You please don't forget that you are working under this assumption, which might be true or not. And at the end of the day, we'll find a way to check it. We also have the ingredients at the end of the day to check whether we are doing well or not. And that will be a very interesting part of our day. Okay? Now, so this is, I have numbers which incorporate the heteroscedasticity, and from theory, I know that, let me go back let me come back to the beginning. We said the GLS expression is like this, and the standard errors, the variance square matrix of the GLS estimator, should be taken from this matrix. So what I do next now, I will replace the big sigma here with the expression with the small h, capital V, and I get also, I have an expression for say, the variance square matrix of the feasible GLS estimator will be the H, scalar H, times the following stuff here. You will say, why h is not 1 over h? Please remember that you have, say, inverse, okay? So it will be h. And we know the guy I'm touching with my, no. Okay, I know the guy I'm touching with my hand. No, okay. I know this guy here, the one, I know this matrix because data. If I can compute, if I can use MATLAB or R or whatever, forget about stata. But if you can write matrices, you can compute this quantity here. You have a problem with the H. But, well, come back to the OLS estimator. What you do in order to compute standard errors with the OLS? Let me just, I want to tell you that I'm not saying strange things. I'm saying, now I'm telling you things that you know very well, because we know, come back to the OLS theory, and you know that the variance square matrix of the OLS is given by, let me find it, please. Okay, this expression here, and I said, if you want standard error, what you have to do? You replace sigma square epsilon with its estimate, and then you have everything. You have to tell your program, you have to tell MATLAB, okay, that is a matrix, take the elements on the main diagonal of that matrix, take the square root, and those are, they call the standard errors. We can do the same here, because, where is it? Here. We can do the same because we have, say, we have this matrix here, okay, inverted, and how do we estimate this scalar h? I simply apply, say, what was the estimator of sigma square epsilon in the OLS? It was simply the sum of square residuals. But in computing residual, we use the OLS in the OLS world. Now I'm using the sum of square residual, but I'm using the feasible GLS. This is a number. This is, you can see this number. There is no unknown. There's no h here. So I can get an estimate of h, and I have everything. I'm using under the assumption. Please don't forget that we're working under the maintained assumption that, say, the heteroscedasticity is explained by the the variability of CO2 emission depends, in a sense, to the to the variability, in some sense, to the square of the expenditure of the family. The larger the expenditure, the larger will be the variability of CO2 emission. Think about it. It's not a very unreasonable assumption, but we will test it at the end of the day. Okay? Not the end of the day. We'll test it in a few minutes. Okay? Again, I will make a break around 4. Today we start a little bit later, but around 4 we'll make a break and blah, blah. But let me now go to the point. And this is one way to go. Now, the point is, how can I do that in Gretel? And that is the beautiful thing. So that's why you find here alternative but equivalent way to go. And if you understand this, you have done 30% of applied econometrics part 1. Please believe me, okay? At a given point, I will ask you an act of faith, but you should not, no faith in econometry. You should prove what I will say to you. But if we want to make the proof, it would take, say, hours to us. And so at a given point, you have to believe to my words. Otherwise, if you don't, as it should be the case, you have to prove it. Okay? But let me go the alternative way. So this is my regression model. My starting regression model was this one. Let me just to recall you. This was my regression model where I said, I am quite sure I have heteroscedasticity because it's almost impossible that the variability of CO2 emission is constant across, is the same across 11,748 households. Okay. Now, what I do, I come back to my question, and you know that from very basic, I have to stand up a little bit. I am a runner, so I cannot sit all the time. Not an important runner, I mean, just a... Okay, now, can you see it? Let me, if I can see from the... Okay, you should see. Okay, this is my, I have my regression equation. You should know this should be 2, x2, comma I, okay? Just to, I have written very quickly. But you know from the algebra that when you have an equation, you do something on the left-hand side, you can do the same on the right-hand side. The model is not changing. This is what algebra says, okay? So what I'm doing now, I say multiply on the left and on the right by what? By 1 over standard deviation, sigma I. Okay? I can do that. And so while I'm doing that, what is the advantage of this? Now, you can consider the novel error term of this model, this ratio here, okay? Now, I want to compute, say, try to compute the variance of this novel error term, okay? I go to compute the expected value of the ratio square, which is the expected value of square numerator over square denominator. Okay, guys? Sigma square I is a number. It's not a random variable. A random variable is the error term, epsilon I. So I can shift this guy outside the expectation. So in a very mechanical, I'm going on in a very, very mechanical way, okay? And you realize that basically for I running on family one, household 1, 2, 3 until 11,000, blah, 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 I have the variance of this error term here is equal to 1. So I have induced homoscedasticity with this simple operation. I have standardized it. I divide, let's say, both sides of my regression equation by 1 over variance. Okay? Now, at this point, if you agree on this operation here, if you agree on this, now let me come back on my hypothesis, the one I did on heteroscedasticity. Remember, I said sigma square I depends on the data, in particular depends, it's proportional up to this H component, is proportional to the square of log expenditure, okay? Now I'm using, what I'll do next, I will replace the sigma I here, 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 and here with what? With this expression here. So this model becomes 1 over, unfortunately, with my, the program I use to write equation does not allow me to do the symbol of square root. So I have to rise to the power 1/2 to make square root, but should not be a major problem. For people taking calculus, okay, at the master program should not be a problem. So this should be square root of h xi square, square root of h xi square, blah, 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 okay? And you immediately see this is an equation. I find 1 over h, I find h here, h here, h here, h, so I can simplify. My model becomes like this. I'm killing the h again. You remember that we, at the given point, we kill at the h from here and we get this expression. I'm doing the same here, okay? I'm roughly doing the same here. And now you understand that since, I show you, since the log of total expenditure is positive, I show you very quickly the data. All the 11,000 blah blah household have positive total expenditure. So if I take, say, the square root of a variable to the rise to the power the result should be the absolute value of a variable. But since we are dealing with positive, all the x's are positive, so this number here will become xi. 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 Are you following me, guys? It's very important that you stay with me, okay? And now let me define why I star this ratio. Let me define x. Let's xi star this ratio here. Of course, xi over xi. This should be 2. Sorry, it should be x2 high. Okay. So this is simply 1. So I have a new model. The transformer model will be yi star b1 x1 xi star b2. Now you know that b2 coefficient now is the constant of this new model. You know, it's amazing. I have xi over xi, so it simplifies, and then I have epsilon I star, okay, which is given by this ratio. And this is something that I can take to the data. This is something I can deal with Gretel. I will show you now, because I simply have to build the ratio between CO2 emission over log, so it will be the log of CO2 emission over the log of household expenditure. Also interpretation, economic interpretation, this y star you have on the left-hand side would be the CO2 emission per unit of expenditure. Okay. The new regression, this novel regressor xi star will be the ratio 1 over log of total expenditure. Okay. New intercept and this error term. So I can run it on Gretel. I will show you. But it is important that if our assumption about, don't forget, never forget this assumption, we are working under this. This is the crucial part. Okay? So, is this model, what should expect homoscedasticity or heteroscedasticity in this model? Well, let me check the variance of this error term. So I'm computing the variance for the moment, conditioning on the household expenditure. I'm computing the variance of this term here, okay? So it will be the variance of the following ratio square given xi, that it will be the expected value of square numerator, square denominator, given xi. Now we have been discussing the property of conditional expectation. We said, look at it, why I'm shifting xi outside expected value? Because I'm conditioning with respect to xi. So it is unconditional with respect to the regressor is as if I am treating the variable as a constant. So that's why I can shift this term here outside the expected value, and by magic, no, not by magic, by simply math, we have that in this model, I have homoscedasticity because the variance, for the moment, the conditional variance of this error term is equal to h. Applying the law of iterated expectations, and if you say this guy is going too fast for me, no, you have to know the law of iterated expectation. When I say that, something must be, you have to follow me. So by the law of iterated expectation, I can conclude that also the unconditional variance of this error term is equal to h. So at the end of the day, my story is that in this model, I can estimate what are the parameters in this model. B1, which was the constant in the original formulation, but now it's a slope parameter, as you can see. B2, which was the crucial slope parameter in the original formulation, but now it looks like is a constant in this transformer model. And finally, what is the other parameter? Is the h, which is the variance of the error term, but you know, h does not depend on I. So I have homoscedasticity elasticity here. Please, there is no magic. There is only this assumption here. This hypothesis is crucial one, and I can run it I can use Gretel now. I will show you now, and at the end of the day, we can check whether this hypothesis here is true or not. Captures the heteroscedasticity of the data well or not. What can I do indeed to check that assumption? I run this model by OLS, so I simply need to build this new dependent variable, this new regressor. Okay? What is the first check we typically do now? Please. Yeah, excellent. We run the white test, and if we don't reject the null of homoscedasticity, bingo! It means that we have captured this assumption, this hypothesis. I mean, it's a good explanation of the way the heteroscedasticity works across the 11,748 Italian households. Now I will show you in Gretel, and then we make a break. Are you following me, guys? Did you get the point? This is crucial. If you want me to make one step behind, please let me know. And let me say the final statement would say, okay, what is the relationship between what you show us before, the feasible GLS, this number here, and what you have done here, and what you're doing with this transformation? The answer is that it's possible to prove, but you need some algebra, that you're doing basically the OLS estimator you get from this transformer model is the same as the feasible GLS you got from here. Of course, I understand that now, in order to believe my last statement, you need to make an act of faith, which you should never do. But if you want to prove that, it takes time, and we don't have so much time. So I ask you to believe me that about these last two lines, it is possible to prove that the OLS of these parameters in this transformer model is the same as the feasible GLS that we saw before. We are doing the same thing from a computational point of view. Now, before stopping, I want to show you how it works on Gretel. But what I have to do in Gretel is the following. I have to define a novel regressor, which is the CO2 over log of household expenditure. I have to define a new regressor 1 over log of expenditure. I simply run this. I run OLS, and I run the white test for homoscedasticity. Okay, this is exactly what I'll do now. Okay, then I will send you at the end of I will send you the script. Okay, so don't worry about that. So I go on the data, and I define the following. Now I add a new variable, my y. My dependent variable will be the ratio between the log of CO2 emission, which was this one, over the log of expenditure. So I'm computing let me call it white star, so you can understand very well, okay, what I'm doing. This is the white star, the novel dependent variable after my transformation. After my hypothesis on heteroscedasticity, I transform my model in this way, okay? So, okay, and I have this new white star, something like this, nothing special, okay? And then I have to define the second regressor, this one. I want to define this regressor here, okay? So what I do is I define new variable, I call it x star, is equal to 1 over the log expenditure, okay? And that's it. Now I say model, ordinarily square. No, my new dependent variable now is y star. And my new, let me move this away. So my new regressor was x1 star, okay? X star, sorry, X star. That was, I did some computation before, X star. And I also need a constant. Do you agree on that? This is beta 1, this is beta 2. I click OK, and I get the following estimate. This negative, okay. Please recall that now the parameter we're looking for is not this one, it's this one. It's the constant, the beta 2 is the first one, which is very similar to 0.62 we saw before. Test heteroscedasticity, Y test. Let me go on the bottom. Let's follow the mechanical rule that we know. Let's prefix as it is standard 5%. My test statistic is 5.91 with a p-value of 0.052. It is borderline, very borderline, but we don't reject the null hypothesis of homoscedasticity, which is good news because basically I got I modeled the heteroscedasticity quite well in this large sample. And I have computed, at the end of the day, the important thing, I have computed a feasible GLS estimator, if you believe to my last 2 lines in the file I sent you. Okay, guys, we make a break. We'll start at, let's do like this at 4:30, okay? So break.
Sorry, one question.
Yes. Go, please go.
So if we accept the null, that means that our model was heteroscedastic?
No, homoscedastic. The null is homoscedasticity. So means OLS is fine here. Okay. After our transformation, we run OLS, which requires, which is based on homoscedasticity, and the test supports the homoscedasticity assumption. Because please recall that even if Gretel says the Y test is for heteroscedasticity, the null hypothesis, the hypothesis we are testing for is homoscedasticity, okay?
Okay.
Okay.
Thank you.
You're welcome. Are other questions from the audience? Okay, so we can have Okay, so we can start. During the break, I get a question from the audience. So, can you better explain why you have divided, say, the regression model by sigma I, by the standard deviation of the error term? The answer is the following. Imagine that when you should know what the meaning of standardizing a random variable. It means I want the random variable to have expectation 0. So you take a random variable minus, on the numerator you put minus expected value, but the error term, the expected value is 0. So I don't put anything here. And I have divided by the standard deviation. Because I know that now this novel random variable by construction has variance 1. So by this simple operation, I standardized my regression model such that I switched from heteroscedasticity to homoscedasticity. Of course, I need at a given point, there is nothing, this is simply algebra. If I don't say anything about sigma I, this is completely meaningless. So that I had to also to complement this algebraic operation with the following assumption. This is the crucial part. My assumption about the heteroscedasticity was crucial here. Okay, that is and under this assumption, of course, what I've done was simply to replace this standard deviation with what my model implies for the standard deviation. And the important thing is that my model implies that the variance depends on observable variables, on observations. Otherwise, I can do anything. So that the modeling, say the heteroscedasticity in the setup, that is why I've written, say, I have a model for conditioning with respect to x, means that I have a model where the variance depend on x. This should be more or less clear, okay? Now, yes, question?
Is there any other assumptions? Can we make any other?
Yes, of course, depends on your knowledge of the phenomenon, but of course, what you put on the right-hand side must be observable. You need data, otherwise you can't do anything, but depends very much, for instance, could be that depends very much on your knowledge of the phenomenon. So since in this case, this is the variance of the error term in a model, you could interpret this is the variance of CO2 of the log of CO2 emissions once you control for household income, could be explained by, depends on your theory, I would say, okay? This is a very simple way to go. Typically, a very simple way to model heteroscedasticity to associate the variance to the square of some of the regressors, but it could be any variable, any observable variable, okay? So, of course, I will stress it several times. You need to be an expert of the phenomenon under investigation. Otherwise, you say many silly things. Okay, you have to be an expert. Now, I want to come back on the slide on our program, and our program was here: properties of the LS estimator. So. This will not be very exciting, I can imagine that, but it's something that we have to do. We cannot skip it. Oh, sorry, I have to go to the slides. Here, okay. So, we already said something yesterday, so I will come back where we finished yesterday, okay? Which was here. And it's very important that today you also understand one concept. Okay, so full screen again. Very quickly, we already said that yesterday. We have been talking, and I need to to bother you, to stress you about the properties of the LS estimator, because if you understand that, you can manage. Say the basic econometrics. So in the classic linear regression model, big sigma like this, okay, We know that the OLS estimator is given by this expression, and we know the estimator of sigma square epsilon, which is an average of square residuals, okay? Of course, you understand that now, think about the example of the 11,748 households. You understand that divided by n or n minus k, where k was 2, is completely, I mean, does not change very much, okay? Now, we said yesterday that when we focus on properties of small sample properties, we try to prove that, say, the expected value of the estimate is centered on the true value, and we would like the variance square matrix as small as possible in matrix sense, which means the best standard error we can ever get, okay? And yesterday we did the following, we finished at this point, if you remember, was we did some, we said, if you take this estimator, if you replace y with the model, with this expression here, evaluated at the true parameter beta 0, after some algebra, some computation, but this is simply algebra, okay? You end up with this expression that your estimator is equal to true value plus something. And I said yesterday, it's quite clear that this something here makes the difference, determines the properties of the OLS estimator. And we said yesterday, again, if the x, which is not our case unfortunately, but if the x were deterministic, if the column of the x matrix would be deterministic column, not realization of random variable, you immediately understand you can apply the expected value here of beta hat would be true value plus, if the x are deterministic, I can shift outside the expected value, and I will get expected value of epsilon, and I get that the OLS estimator is centered on the true value when the regressors are deterministic. For instance, if in your regression model you have just a constant, or I don't know, we'll discuss dummy variable. Have you ever heard about dummy variable? No, it's, yeah? Yes, a variable that take value 0, 1. Just to give you very quickly the intuition, imagine that, coming back to our Kuznets model, imagine that I have some idea that household from the north of Italy might be different, say, from the point of view of CO2 emission from the household from the south. Okay, so look at the data set just to give you the intuition, because I don't know if we have the time to talk about dummy variable, but in the data set, for instance, I have this, you will find in the data set I sent you, this variable north. North will be, you will find a set of 1, 1, 1 or zeros. Basically, you find the 1 are associated with the households that belong to the north of Italy. At a given point, you will find zeros. Oh, come on, where are the zeros? Okay, let me go faster. Yeah, fortunately, also have. Okay, the ones, so this is a variable, a dummy variable is a variable, take 1 if the household belongs to the north, according to some classification, okay, and 0 otherwise. In the data set, for instance, you find that you have a dummy for center of Italy. So, of course, where you add 1 before, you must have 0 now, because a region, household either belong to the north or to the center. So you at a given point will find 1, okay, somewhere. And also you have south. Of course, it will be, okay. I have a question to you now, just this is a curiosity, even if I spend my time, but this is important. Imagine that, think about this stupid regression model, okay? I do the following regression. Ordinarily square, I said CO2 emission, and I have a constant, then I put north, I have constant north, center, and south. So I have included 4 deterministic variables. Those are deterministic, a dummy variable. I have a constant 1, 1, 1, 1, 1, then I have north, 1 only households associated with north, South, I have one only for households that belong to the south, and center, blah, blah, okay? Now, my claim is that if I click OK now, Gretel goes crazy, and the question is why? And let me give you just an hint. Think about the column of the big X matrix here now, the regressors. You will find, say, the first column will be, you have a constant, so the first column will be 1. Do you agree on that? Second column will be a column with zeros and 1, depending on whether the household belongs to the north or not. Okay. A third column will be again with 0 and 1, depending on the center, and the last column will be again 0 and 1, depending on. My claim is that if you sum the column north plus the column center plus the column south, what we will get? Only once. So think about the X matrix. I said the columns must be linearly independent, which is not our case, because the column 1, 1, 1, 1 can be obtained by summing column number 2, 3, and 4. And the X matrix is not, has not full column rank, because one column depends on it's a linear combination of the other 3. And in that case, so it's impossible for Gretel computing X prime X inverse. Indeed, I click OK, and he also omitted due to X. So what he said, dependent variable, and what he has done, he has killed by construction. This is wonderful. I didn't know this. He has killed one dummy. He has killed the south dummy because of that, he said omitted due to exact collinearity. Collinearity is when one column on the X matrix is kind of linear combination of the others. So if you want to model, when you are dealing with deterministic variable, in particular dummy, you have to think about that, okay? I repeat the point, it is important. The column of the X matrix must be linearly independent. In my specification, if I have a constant, north, south, and center, they are not linearly independent because one of the 4 columns would depend on the other 3, would be linearly dependent on the other 3. That's why you have to kill one column in a regression model like this, okay? But we'll come back on. Let me stick. I'm kind of procrastinating the hard job we have to do. Okay. Now, okay. So this term here makes the difference, and now we are going to study how to address this term. Okay. Now, also, let me, again, I will repeat several times, matrix notation, index notation. So you understand that, why is it useful now that I rewrite this thing like this? I use the summation notation, okay? Because it is with the summation notation, it's very convenient since I have inverse here, putting 1 over n here, and 1 over n here, okay? And why I've done this is that my point is that the following quantity, which is equal to this quantity here, from an algebraic point of view, they are the same. We can have a situation where, we can have a situation where the expected value of this term is different from 0, but if we send n to infinity, and if we can prove under some condition that this term converges to something, this term converges to something, we have a situation where even if the OLS estimator is not centered on the true value, but if we send small n to infinity, and if this term in particular converges to something which is close to 0, we have that the beta estimator, when n goes to infinity, gets closer and closer to the true value, which is yesterday we say that is the property of consistency of the LS estimator. What I'm trying to say, the message I'm trying to deliver to you is that we may have, say, a biased estimator on a small sample, but the bias could disappear when we send n to infinity. And so we have to study this situation. We have to be aware how to deal with this situation, okay? So that's why I say we are concerned with the properties of the LS estimator, not only in finite samples, so when we treat n as finite number, but also when we make a logical experiment, which is sending n to infinity, which is the case of large sample properties. Okay? So that's why we distinguish between finite sample and large sample, okay? And again, the properties must be discussed on a case by case, Now, finite sample properties. Now, we want to compute, typically, given our estimator, we want to evaluate the expected value of beta, because if we prove that the expected value of beta is the true value, we are happy, okay? We do, in order to compute this quantity, and since very seldom our regressor will be deterministic, as in the example before, we do the following trick. I mean, we first compute the expected value of beta at given x, conditioning on the random variable we have inside the X matrix. And now I will come back seriously on this concept, so don't worry, okay? And then, by applying the law of iterated expectation, basically, I use the following. Basically, what I do, I focus on this, and if I can compute the one I am selecting with my hand, then, using the law of iterated expectation, I can compute the unconditional expectation. So in our case, it's considerably simpler to focus on the conditional expectation, and then once we solve for the conditional expectation, we move to the unconditional one by the law of iterated expectation. It is a very important law, we have to know it, okay? Now, I want you, I mean, this writing here could be, I want now to focus on the meaning of this term here. What's the meaning of that, okay? Because once you understand that, sorry, we can do what we want. Now, let me consider the following example. Imagine that V is a random variable with V1 and V2. So it's a bivariate vector, two random variables. And imagine that M is a matrix containing random variables, okay? So nothing, something that we already have met during our classes, okay? It seems something very difficult, but it is not. Something that we can manage. Now, the definition, when I say I'm computing the expected value of V given conditioning on M, okay, I mean the following, the meaning is the following. I'm taking the expected value of V1 given all elements on the M matrix, expected value of V2 given all the random variable in the M matrix, okay? So, if you want just blow up this concept, you have basically the first term here is given by expected value of V1 conditioning all the random variables in M, and the same for V2. It's not difficult to understand this, but this is some important implications now. Now, okay, so let me compute now the expected value of the, let me, okay, I want to compute the expected value of my estimator conditioning on X. Now I know the meaning. This is a vector, remember, beta hat is a vector, our parameters, and we are conditioning with respect to the matrix X. You will say, well, but if you have a constant, there will be a non-deterministic variable. The first column will be 1, 1, 1. You're right, but the other variables are stochastic variables, okay? And so we know the meaning of this writing. But now I replace beta hat with this expression, okay, conditioning on x, and now I move on with the properties of conditional expectation, which conditional expectation is linear, exactly as unconditional expectation. So what I have to compute is the expected value of true value given x, and you understand that beta 0 is the true value, is not a random variable, so I have beta 0 here, okay? Second term, I have the expected value of this term here given x, and what I have written here. Okay, guys? Now, second step is, should be clear now that since I'm conditioning on the random variable in the x matrix, I can treat this x prime, x inverse x prime as kind of constant. I know there are random variables, but I'm conditioning with respect to the x. So what I can do next in the third line here is what I've done was shifting this term, the x's, outside the expected value, and it remains the expected value of error term given x. Okay, and now I'm very close to the point, because if we are in the situation where we can claim that the expected value of epsilon given x is equal to 0, so we are killing this term, and we have that the expected value of beta hat given x will be centered on true value. By applying the law of iterated expectation, we find unbiasedness. So this is condition. The validity of this 0 here is crucial to prove that the OLS estimator is centered on the true value. Okay? Indeed, and you have the argument here. If you can claim that this term, this expected value is equal to 0, then it means that basically we are killing this term here. This will be 0. And so I get the expected value beta given x is true value, and then by the law of iterated expectation, I get the result. But on the other hand, if I know for some reason that this term here is not 0, but it's different from 0, then you should agree with me that basically I have that, it means that I'm not killing this term, this bias will remain there, because I'm not killing this term. And of course, I have a situation, a setup where the expected value beta hat given x will be different from the true value. And by the law of iterated expectation, I am in this position here. So summing up, and this is the point, it's very important to decide, to know when we can claim that this term is equal to 0 and when this term here is different from 0. That's make the difference. Now, my next step will be now, I want to reason with you, want to discuss with you when we can claim, when we can safely claim that this is 0, fine, okay. And on the other hand, I want to discuss with you one case where we cannot claim that this object is equal to 0. And you know, the implications, we know that now the implication on the finite sample property of the OLS estimator. Okay? And I will provide you with examples. So, what is the meaning? I want to come back on the meaning of this expression here. And I want to discuss with you when we can claim that this quantity is equal to 0 and when it is not. Okay? Recall that I have given the definition 2 minutes ago. So whenever I write expected value epsilon given x, I mean expected value of error of the first unit conditioning of all the variable in the x matrix. Expected value of error on the second unit conditioning on all the variables in the x matrix, and so on. Okay? Keep this in mind. This will be important. And just, it is the definition I gave you before, the general one. Now I want to consider an example with you. Okay, which is the sample we saw, the Kuznets, very similar to the Kuznets linear approximation of the environmental Kuznets curve. Okay, the model was this: CO2 I runs over individuals, countries, or households, or in the previous example, and so on. Okay, we have a constant, and we are say, imagine that I have disposable income as the second regressors. Okay, and in order to simplify, I don't have now 11,700 households, but let me just add 3. Okay, so it will be writing now the X matrix. I'm using 3 because the X matrix, you understand, now is given by first regressor constant, so 1, 1, 1. Second regressor will be disposable income of first household, disposable income of second household, and disposable income of household 3. Very simple to write X. Okay? Now, what's the meaning of expected value of epsilon? The error term given X will be, we know, expected value of epsilon 1 given X, expected value of epsilon 2 given X, epsilon 3 given X. And we know that it means what I'm computing, the expected value of, this is the error term of the first household, okay, associated with the first household. I'm conditioning with respect to, okay, 1, 1, 1 doesn't matter. I can, if you condition with respect to deterministic, you are not conditioning, okay. What matters is disposable income. So I'm conditioning with respect to disposable income of household 1, but also with respect to household 2 and 3. So if I put this term equal to 0, it means basically that, say, not only the disposable income of family 1, of household 1, I mean, does not affect the expected value of the error term of household 1, but also disposable income of the second family and the third family. The same argument, I mean, if I say that this second term is equal to 0, I have basically my point is that the expected value of the error term of the second household, conditioning of the first household, second household, and third household is equal to 0, and so on. So if I put the first term here, this guy equal to 0, or if you like, this one equal to 0, so the slide said, if this is equal to 0, it means that the expected value of the disturbance associated with household 1 is not influenced not only by total expenditure of household number 1, but also by total expenditure of all the other households in the sample. Okay? By construction, by definition. And the same for epsilon 2, and the same for epsilon 3. Okay? Now, in general, when we have cross-section data, the assumption that this term is equal to 0 appears reasonable. It's something that we do. Typically, we don't have, if I have no argument to claim that if, say, the error term, if the error term conditioning on the regressor of the first household is equal to 0, I have no claim I have no argument to claim that it will be different from 0 if I condition with respect to the second or third household. So, in general, with cross-section data, the assumption that the expected value of the error term is equal to 0 is something that can be defended. We believe it. We believe to it. And so the implication is that, coming back to this expression here, the one we saw before, so we can say this term here is equal to 0 with cross-section data. So in our example of the 3 households or the 11,700 households, we can safely claim that this term is equal to 0. So we have that the OLS estimator is centered on the true value. It's the unbiased property holds. And now the interesting part will be when it is violated, when it does not hold. That will be the point, you understand? And let me consider now example number 2. in example number 2, what I'm doing now, I have a similar example, but now I have time series. Imagine that I am considering a single country, Italy, for instance, and this is a model which explains the dynamics of the evolution of CO2 emission in Italy over time, okay? And according to this model, CO2 at time t depends on a constant, depends again, think about the environmental Kuznets curve, so it depends on, say, the income of the country, the average income of the country at time t, but now the novelty I have included, you know, I've included, say, the dependent variable CO2 in the previous period as a regressor. Why should I do that? You know, it's very reasonable to, if I to model the dynamics over time of CO2 emission, that the CO2 emission this quarter must be somehow related to the CO2 emission in the previous quarter. And the beta 2 parameter here captures, say, the dependence of today from yesterday. Think about, say, consumption. If you have a model for consumption, you know, agents have consumption habits. So what I consume today depends in some sense of my previous consumption and so on. So in models, in time series models, it's very, I mean, if I want to forecast next period CO2 emission, I will base my forecast on today emission. You understand? So imagine that we have a model like this, and we'll call during our, you will deal a lot with this class of models in the second part with Professor Panagonitis, okay? I call these models dynamic model. Why do you call it dynamic? Because we have a dynamic model when you find the dependent variable among the regressors with t minus something. Because the past influences the present. I need to drink something. I make a very short break. I go to get some water, okay? Sorry. Should not be COVID, no, don't worry, just I make a very short break, okay? Now imagine that this is again my model, okay? And again, I'm considering 3 time periods, okay? To simplify, yes. Yes, yeah, you're right. Okay, you're right. This should be 3, beta 3. Sorry. Okay, this should be 3. Thank you for pointing out. So in this case, what is the big X matrix? Again, first column will be 1, 1, 1 because you have a constant. Second column will be disposable income in period 1, 2, and 3. Last column will be CO2 emission at, say, initial time. This start at time t equal to 1. We need some CO2 emission at time 0, initial condition. And then I have CO2 emission time 1 and 2. And this is the big X matrix, okay? Now, let's focus, and this is crucial now. Again, what is the meaning of the expected value of the error term given X? We know that if this term is equal to 0, the Euler's estimator is centered. Otherwise, it will not be centered. Now, think about, let me take an example. Let me consider the following guy here, okay? And please follow me, this is crucial now. Let me focus on this. So I'm considering the expected value of the error term at time 2, conditioning on X. It means and conditioning with respect to all random variable in the X matrix. Okay? In this matrix, I also have CO2 emission at time 2. Think about that. And indeed, the slide says, okay, it's exactly the example. Think about the model for CO2 emission at time 2. According to our model, CO2 emission at time 2 is given by beta 1 plus constant plus beta 2 income at time 2 plus beta 3, this should be 3, okay, CO2 emission time 1 plus error term time 2. Okay? I not invented this model. This is my starting model, this one, when t is equal to 2. Okay? And I am to the point now. Because I have the expected value of epsilon 2 conditioning on some variables. Among these variables, I have CO2 emission at time 2, but CO2 emission at time 2 is a function of epsilon 2 itself. So I have the expected value of epsilon 2. This is written very well in this line here. We are facing the situation where we have the expected value of epsilon 2 conditioning on many variables. We have many random variables here. But among the many variables, we also have epsilon 2. It's not a magic. It's simply because of the dynamics. Okay? So, and this term here cannot be, if you take the expected value of one variable conditioning on itself, it can never be 0. So, and of course, the same argument apply if you consider I just consider this very, do the exercise. I can do this, you can do the same argument with the expected value of epsilon 1 given this matrix, but not with the last term here. Think about it. You will find that inside the X matrix, there is no epsilon 3. So, in this case, we are in a situation in the dynamic model. By dynamic model, I mean a model in which the endogenous variables enters among the regressors with time t minus something, okay? In that case, we have the following condition, which implies that the Euler estimator has a bias, because we are not killing this term. And this object here measures the bias. But in cases like this, we still use the OLS model, even if this term, if we have a bias, we still continue to use in this model, in this dynamic model, we can still estimate the parameters B1, B2, and B3 by where is it? No, this one. Sorry. This model, we can still apply OLS. Why? Because in that situation, we prove that we can prove that if we send n to infinity, if we have a large sample, something happens to this term here. So in finite, if you treat n as finite, you have a bias. But if you can send n to infinity, I will show you that the bias disappears. And so let's make some summary, okay? So finite samples, we have that the OLS estimator is centered when you have this condition, and it will be distorted when you have this condition. Okay? And the same properties of beta hat will be inherited by the sigma square epsilon estimator. Okay? Now the last effort before we make an addition, a break, then we go to the end. I want to, we have been talking a lot about the variance of the OLS estimator given X, because it is the matrix from which we take standard errors, right? Now I want to, and we said the variance of beta given X is given by this expression, this one, is given by this expression here, okay? We have been discussed it several times. Now I want to give you just a formal, you have the ingredients to derive it formally. It's not difficult. Again, we start from our starting point is estimator is true value plus something, okay? Now, what I do, I apply the variance of beta hat given X, again, okay? So what I do, I plug in, I replace beta hat with this expression here. So I have this object here, okay? Second step, beta 0 is a true value, is a deterministic vector, it's not a random variable, so the variance of a deterministic object doesn't matter. That's why me moving from here to here, there will be no bit 0, okay? So I end up with the following expression here, okay? And what I have done, which seems to be very, very complicated, is a very simple thing. I have applied what econometricians call a sandwich rule, and let me write it on Word so we can slower a little bit. The general rule is the following. Okay, imagine that A is a matrix, no random matrix, so the elements are just real number. X is a random vector. So when you have to compute the variance of A times X, so come back to the word, imagine that A and X are scalar. A is a real number, X is a random variable. What you typically do, you shift A outside variance square, because it's a variance. Now I'm going to generalize that, and the sandwich rule says, okay, this is equal to equal to matrix A times the variance of the random variable X, the variance of X times the matrix A transpose prime. So why is it a sandwich? Because you have bread, and something inside. Okay. Now, one thing you can do is that, imagine that you have a more complex setup like this. Imagine that you are computing, say, W, X conditioning on W. Okay? So I told you several times, when we condition, so W and X are two random variables, okay? I already told you, when we condition with respect to some random variables, it's as if we can treat those random variables as constant. They are not constant, but if we condition upon them, it is as if they are constant. So, by the sandwich rule would say that in this case, I can write W, the variance of X given W, times W prime. Again, I am applying the sandwich rule, but I am in a conditional model. Let me write like this, times, so you can better understand. Okay? Now, it was apparently, it was very difficult because we are here. I'm computing the variance of this object given XO. Basically, you understand that now I can shift, I'm conditional with respect to X, so I can treat the X as given. So I can shift the X's outside the variance, but I have to apply the sandwich rule. I am exactly in this case. Probably this confuse you. Let me write like this, okay? So let me change notation so you better understand what, okay? So I don't want to, I want to simplify your life. So just let me change notation, okay? Okay, think about that. You have the variance of X times Y conditioning on X. So I said the X can be treated as given because we are conditioned with respect to X. So I can shift the X outside the variance, but recall it's a variance, so we have to compute square. So I need to apply the sandwich rule. This is what I have done exactly here. No, not here. I have basically a condition with respect to X. I have the X's, epsilon, so I can shift this term. Let me select it. Let me color it. No, without epsilon. Okay, it's possible. It's not possible. Okay. So let me bet lens. Okay, I can shift this term here on the left, and it is what I have done here. And I can do also on the right, but prime, transpose. Yes?
But you can shift it outside because it's a random variable, you are conditioning
yes.
on it.
X.
Yeah, but in our case, X is the regressor, so it's data. No?
Yeah, it's a realization of the data. When you think about the data, you have to think about realization of random variable. What is
if I think of realization of a random variable, I can treat it like a constant.
When you because you are conditioning on that, you are conditioning. When you condition, yes, it's still a random variable, but since you are conditioning, you can treat like similar to a constant. So, but if you, you can take, say, this rule as the leading one, okay? And so by simply algebra, I have this term here. This is the same term prime according to the sandwich rule. And at the end of the day, it remains inside the sandwich, this expression. What is this expression? This is simply our big sigma matrix. The big sigma matrix in the classic linear regression model is scalar sigma square epsilon time identity. If you plug in this term here, you end up with this expression here. And if you like notation with indexes, you have this, the other way of writing. And now you know why we say we take standard errors from this matrix. Simply because it is the variance matrix of our estimator. Stop. It's not a mystery, it's not a magic. Okay? Something that we can control for. And we don't prove it, but it's possible to prove that or any other linear estimator alternative to the LS as larger variance will give you larger standard errors. And then now I have a set of, we can stop a set of results which make the summary of what you have done so far. Okay, so result 1 will be summary of what we said, result number 2 the same for sigma square, and so on. Okay, now we make a break, and then we continue with the novel. Now with novel things is that so far we have not mentioned any distribution of the variable. Now I'm putting into play into the game also the distribution of the variables. That will be very, very important for where we want to test hypothesis. But we can make it's 520. We make 10 minutes break and then we go. I'll try to finish before 6 o'clock, okay? But we do need 10 minutes of break.
You want to